So next, we move on to Feynman diagrams. Which is a very intuitive and nice way of computing these endpoint functions in perturbation theory. So what we want to do is that we want to calculate, this thing. So these are Heisenberg operators. And we can only do this as a perturbative series in lambda. So we want to calculate this as a perturbative series in some coupling constant lambda. And lambda, then we have to assume, is much, much less than 1. Otherwise, the perturbation theory, the perturbative series will not converge. Of course, lambda has to be positive as well. Otherwise, we saw that our Hamiltonian will not be stable. It will not have a vacuum. So let's look at this. So we want to calculate these kind of things as in a perturbation theory expansion. So we want to be able to calculate things like the time-ordered product. So this is in the interaction picture. So let's just take, say, 4 operators. So what is this going to be? Well, we saw that this is nothing but this object. So this, what we can say is that we can express that result graphically. So how do we do that? If you look at this result, we see that we have a Feynman propagator going from the space-time point x1 to x.2. So remember that we had an interpretation of the Feynman propagator as the amplitude of a particle being created either at x1 and propagating to the point x2 and being absorbed there, or vice versa. And similarly, then for this. So we can graphically represent this as a particle being created from the space-time point x1 and then propagating to the point at x2 and being absorbed or annihilated. Similarly, there's a particle being created at point x3 and it's propagating to the point x4 and there it's annihilated. So that's the interpretation of the first term. The second term connected x1 to x3, x2 to x4. So therefore, the second term will have the interpretation where the particle is created at x1 and then it propagates to x3 and it's annihilated there or vice versa. And therefore, x2 will have to be paired with x4. And lastly, the last term is going to have this kind of interpretation. So first, let us label our space-time points. And it'll have the interpretation that a particle is created at x1, it propagates to x2, and it's annihilated there. And the particle is created at x3, and then it propagates to x2, and it's annihilated there, or vice versa. So these are examples of Feynman diagram. So if I'm given a Feynman diagram like this, I can say, okay, all I have to do to reproduce the amplitude for this diagram is to write a propagator with the points x1 between the x1 and x2 times the propagator x2 and x3, and similarly for these terms. So let us now show how to calculate the two-point function as an example. We saw that we can expand this two-point function as a Dyson series And the numerator will be a time-ordered product of phi1 and phi2. So these are interaction picture operators times the time-ordered exponential. Now we are using phi to the power 4 theory, so we're going to write this interaction term more explicitly. And then in the denominator, we just have the time-ordered exponential. We should really use z here and z here. So let's first look at the numerator. So the numerator is, we can expand and then the exponential can be expanded as a power series. So first term is 1. The second term is I times lambda divided by factorial of 4 integral over d4 of z, and then we have phi to the power 4 of z. Then the second order term is going to be minus I lambda squared divided by factorial of 2 and then factorial of 4 squared. And then we're going to have two integrals. One would be over d4z1, the another one d4z2, and then we'll have phi to the power 4 z1, phi to the power 4 z2, and then higher order terms. And then ending with a ket, vacuum ket. So the points x1 and x2, so they're called external points. Because they're outside the integral, whereas the points zi's, which are integrated over in this term, and also the higher order terms, these are called internal points. So we can see that we can now apply Wick's theorem term by term, and then we see that the first term is going to give us, so the first term over here, so this is going to give us the contraction between phi1 and phi2. And the second term is going to give me this prefactor and the integral over d4 of z. And there'll be one term where I get contraction between phi1 and phi2. But there are three ways in this, and then phi z can contract with phi z, and then phi z can contract with phi z. And the three ways where four objects can be divided into two groups, and therefore we have a factor of 3 here. And then we also have another term of the same order in which phi1 contracts with one of the phi z's, and then of course that can happen in 4 different ways. And then phi2 can contract with one of the remaining phi z's, and that can happen in 3 different ways. and then the rest of the phi z's contract with each other. So, and then we'll have higher order terms. So now we can rewrite this. First term is just the Feynman propagator between x1 and x2. And the second term, we can now simplify these numerical factors. We get minus I lambda. There's an integral over d4 of z. And the first term is going to have a numerical factor, 1 over 8 d Feynman of x1 minus x2 times d of f z minus z squared, and then we'll have plus half d Feynman x1 minus z d Feynman x2 minus z, and then times d Feynman z minus z. So diagrammatically, we can express these terms in the following way. The first term, we can just draw it like that. So this is x1 and this is x2. The second term, we can draw it as, this thing is just going to be, again, a Feynman propagator from x1 to x2, whereas this thing is just two Feynman propagators connecting the same point z. So this is the point z. So there'll be this Feynman propagator ending in the same point, and there'll be another Feynman propagator ending at the same point. So that's this term. And then the third term is going to be x1 will be connected to the point z, and that's this factor, and this factor is x2 will connect to the point z, and this factor will just connect z to itself. So this is going to be the third term. Now we see that each of these terms have a numerical factor of the form 1 over s. So for example, this guy has 1 over 8, this guy has half. So this 1 over s, the number s is called a symmetry factor. And the symmetry factor can be calculated from the diagram. And the way to look at it is that you first fix the external points. And then what we see is that at the base of the internal points, for each of the loops we see, what we do is that we just exchange the base of the loops. And if we get the same diagram, the number of exchanges that we can do is going to be the symmetry factor. So for example, for this diagram, we see that we can exchange this guy with this guy, and we get the same diagram. So that gives us a factor of 2. And this loop similarly gives us another factor of 2. So the symmetry factor for this guy is going to be 4. Whereas here we have only one loop, and therefore the symmetry factor is going to be 2. So therefore, we can associate a symmetry factor 4 with this guy and a symmetry factor 2 with this thing.